My name is Sagar Chaki. I lead a small group here called the Cyber Physical Systems and Ultra Large Scale Systems, which is under the Software Solutions Division. And a lot of our work is focused on producing assurance about the quality of software using analytic techniques. And so I have a talk at the end of this session that will expose you to a bigger set of things that we do. It's a broader project. But this talk is actually more focused and was trying to address a problem, a specific challenge of trying to parallelize software model checking. And this was done jointly with my colleague Ari Gurfinkel, who is in the audience, and Derek Karimi. So, as you might know, Linda has mentioned this in her introduction. Model checking is this technique that was developed in the early 80s, partly here at CMU and also in Europe, that essentially is a formal verification technique for systems or models of systems. So you give it, the input is a description of a system in some kind of a finite state machine and a property that you would like the system to satisfy, expressed in some kind of a temporal logic. And what model checking does is exhaustively goes through the system space, state space, and basically verifies along all states or along all paths in the system is the property true. So that's a high level description, and then over the years, the last 3 decades have seen tremendous improvement in model checking in terms of the complexity of the systems that it can handle, from a few tens of thousands of states that you could do in the early 80s to 10 to the 1200 states or even infinite states today. And this has been driven by a combination of 2 factors. One is Moore's law, so machines got more powerful, but we also developed better techniques to reason about systems. So in the early days, the model checkers used to be what is called explicit state. They used to basically think of a system as a graph with nodes and edges and things like that. But then along came something called symbolic reasoning, where you learn to reason about systems using logical formulas. So the combination of those symbolic reasoning and just raw CPU power enabled us to reach to very complex systems. But the challenge is still there. It's an ongoing thing that keeps pushing us to do even better. And so in particular in this project, we looked at model checking applied to software. And this is particularly interesting because the existing software model checkers, or at least the symbolic ones, are all kind of sequential. They do not take into account the tremendous CPU power that we have available today through multi-core and many-core machines or supercomputers. And also because very recently there's been a specific symbolic algorithm called GPDR that was developed to analyze software, and people haven't had the chance to try and take this and try to see if we could parallelize this. So we wanted to take that challenge head on and see if we could make some progress. So what is GPDR? So if you think of software model checking, the classic problem that you're trying to solve is a program like a C program with an assertion somewhere, and you want to prove does this assertion always hold along all executions of the system. So that's the problem that you as a user would try to solve. That's interesting to you. What happens in the back in the engine is for something, if you're trying to use GPDR, is if you take this you take this program and you convert it into a system of equations called constraint Horn clauses. And these equations are constructed in a way that if you can solve them, that is, if you can find values for the unknowns, which in this case are predicates like px, qx, etc., in a way that the value of qx is false, then it turns out that this program is safe. That is, there is no way to reach the assertion and violate the assertion. So that's something we know how to do. So the main thing we want to do is basically create a very fast engine to solve these kinds of equations, these constraint Horn clauses. And that's what GPDR is meant to do. It takes as input a bunch of these formulas, and then it chugs along and says, hey, I found a solution, the program is safe, or no, the program is not safe, there's no such solution, or if there's not enough resources, not enough time or memory, it could give up and say, I don't know. So from now on, we are only going to think about solving basically formulas like this, and not with the understanding that there is a software that we are trying to verify. So how does GPDR do it? It's a classic iterative algorithm for solving systems of equations. So it starts with some initial guess for the unknowns. In this case, there are predicates. In your formula P, Q, R, let's say, you have 3 predicates, And it starts with an initial guess that says, let's say, okay, the predicates are true, everything is related to everything. And then it tries to see if that guess is a true solution of your system. So it can, given a guess, check whether it satisfies all the constraints in your equations. And if so, great, you found a solution. Otherwise, you kind of refine your guess. So you have to say, okay, my initial guess was not correct, and this is why. This is it doesn't satisfy this equation. And from that, you can actually refine your guess. And what refinement really means in this context is you learn facts. You learn things called lemmas. So you say, okay, I know that from my equations, x, variable x, always has to be less than y. So x less than y would be like a lemma that you would learn. So you repeat this process, and along the way, you either find a solution, or you prove that there is no solution, or the third alternative is you show that with this current guess, I cannot decide either way. So it's like I don't know. And if that, if you get to that point, you basically have to restart the process with the next level of the guess and just keep repeating this. And for systems where, equations where variables are finite domain, everything is sort of finite, this will converge to a solution. You can do that. So that is a very high level view of GPDR, very quick. There are lots of details, but I wanted to basically get the idea across that the core of this algorithm are these lemmas, these facts that you learn about your system, and that you keep adding to your knowledge base and keep improving your solution. So how do we parallelize this? So first of all, we looked at an even simpler case of this. We said, let's look at equations where there is just one unknown predicate. And this turns out to be very useful in practice because hardware verification is exactly this. A lot of the hardware verification challenges can be reduced to horn clauses where you are just one unknown. Right? And so there's actually an algorithm out there, an implementation called IC3, which is basically GPDR in the special case of one unknown. And we took an existing implementation of IC3, and we had this basic idea that we are going to run a bunch of them in parallel, and the way they are going to communicate, they're going to interact, is by sharing lemmas. So whenever I run and I learn a lemma, I put it in some kind of a database, and that database becomes available to all the other solvers that are running in parallel. So the idea would be, just let's cooperate by just sharing what we've learned in the form of these lemmas. And more specifically, the way you share these lemmas is actually all of these solvers use a SAT solver, Boolean SAT solver, as a back-end engine, repeatedly calling it to get solutions. And the way you share the lemma is basically you add that to the knowledge base of the SAT solver. So if there's a common pool of SAT solvers that all these IC3 solvers are using, and everybody adds new lemmas into the solver, you're basically sharing the information that you're learning. And the intuition is that would give you a much faster solution than one solver could do alone, right? Because you are potentially leveraging everything that the other solvers have learned. So that worked well with a caveat. So it worked well in the sense that we got good speed ups. And let me just go up ahead a little bit to show some slides. So you see here different columns showing different types of variants of our parallel solver. And you see the mean and the max speed up you got with respect to a single IC3, a single sequential solver. And you can see there was some good speed up in all the cases. And that's great news. So the flip side of that, is great you parallelized this thing, is that actually the solutions, the runtimes are not very predictable. So you take this parallel solver that has some IC3s running in parallel, sharing lemmas, and you run it once, it solves it in 5 seconds. You run the same problem again, it solves it in 50 seconds. You run it again, it solves it in 0.3 seconds. And that was like, what's happening, right? And so what we did was we basically took the runtimes, we took one problem and we solved it 3,000 times using this parallel solver, and we plotted the histogram, and we got something like this. And we got the cumulative distribution function, we got something like this. We did it for another problem, and we saw a pattern emerge. And what the pattern that emerged was that the runtimes of this solver was following something called a Weibull distribution, right? So what you see in red is the idealized Weibull distribution that you get by fitting these numbers to a Weibull distribution. So you can see that in the the CDF as well as the histogram are very close to a Weibull distribution. It's not perfect, but it's very close. And the intuition behind this, so if you look at what a Weibull distribution is, actually there's a theorem in statistics called extreme value theorem, and that it says if you take a number of independent and identically distributed random variables, and if you take their minimum, then that minimum is a random variable which will converge to a Weibull distribution, right? So there is this concept of a minimum of several random variables that's coming into play. And the way this is happening is, if you think about what's happening in this parallel solver, you have 4 solvers that are running in parallel and they're sharing information. If the information they share is only causing a weak correlation between them, is weakly affecting each other, then as soon as you get one solution, one solver says, I found a solution, you stop, which means essentially the runtime is the minimum of the runtimes of all the solvers, right? So in a sense, the runtime of this parallel solver is the minimum of the runtime of all the solvers in this group, right? That's kind of the intuition. It's not perfect because of course they're interacting, they're sharing lemmas, so it's not independent. But we believe that the correlation is very low, which is why you see this kind of a Weibull, right? So what can we do with this? So you've got a good solver which potentially gives you a good speed up, except not always. So the second idea is something called a portfolio. So you say, okay, I've got something that has good average case or good extreme behavior. Let me run many of these in parallel. So now you're using parallel concurrency in 2 ways. You have a parallel solver with a small number of IC3s sharing lemmas, and you have many copies of these solvers just running independently. And as soon as one stops, you say you found the answer. And the idea here is, again, if you have a big enough portfolio, you'll be lucky, and on one run, at least one of those parallel solvers is going to stop in a short time. Right? That's the idea. So again, using the power of concurrency and trying to run a random variable many times in parallel, so that you expect you increase the probability of success. And so the natural question to ask is, how big should such a portfolio be, right? And so one way we pose this problem is, what is the probability if I fix the number of solvers in a portfolio to be m, then what is the probability that this solver will stop in time, its running time will be no more than the expected time of a single parallel solver. That we call that PM, and what we were able to show is that it satisfies this inequality. And in fact, if you plug in the numbers, what you see is an interesting thing, that if you have a portfolio of 20 of these parallel solvers, and if you stop as soon as one of them stop, then with a 0.99999 probability, you are going to find the correct answer in no more than expected time of a single solver, which means essentially by using 20 of these solvers, you are with very high likelihood getting the best expected running time that you could get. So that's one result we had. And so I'll come back to this slide, this table again, because now I can give you a little bit of information. So these mean and max speedups were actually obtained not with a single parallel solver, but with a portfolio of 20 solvers. So we took 20 parallel solvers, ran them, and we stopped as soon as one did, and then we did it for all the benchmarks. We took the mean and the max, and this is the numbers you get. The last column here, IC3 rand, is saying, well, what if you just randomize the SAT solver itself? Let's not do all this parallelization complexity and this. What does this parallelization gain? Let's just randomize the SAT solver, and that gives us some power, and use some portfolio of those randomized solvers. What we show here is that the speed up is very low. It's not, it's like a small percentage. So actually, randomization through parallelization and sharing lemmas gives you a big potential gain in terms of this particular problem. So now the second part of the talk is about how to do it for software. So we've talked about applying it to this restricted problem with a single unknown. How about multiple unknowns, multiple unknown variables? So there we have an algorithm called GPDR, and we spent basically a lot of time taking an implementation of this algorithm and refactoring it in a way that we could then apply this lemma sharing idea, because the current implementation at that time wasn't really made for that kind of sharing. And then we did run some experiments on sharing lemmas between copies of these solvers. And the other thing we did was actually inside GPDR we developed 3 different variants in which GPDR could run, and the details of this are like complex. But essentially there is a priority queue that the algorithm maintains to decide which solution, which item it should process next, etc., which equation it should try, and which solution it should refine, etc. And there are different strategies in which we process this priority queue, and all of them have different performance portfolios. So the thing we had was we had 3 different strategies. The good thing is they're all kind of complementary. We found on a benchmark of examples each strategy you do very well on subsets of those examples. And that means there is enough diversity in these strategies that if we combine them now in parallel and share lemmas between them, hopefully we'll have again the idea that we'll have something that's much better, maybe probabilistically, but still much better than any one. And so we had this toolkit and we had experiments, but unfortunately kind of reached the end of the project and sort of ran out of time and effort. So we have very good promising results for the hardware case, for the restricted case, but not concrete results that we can share for the more general software case. So that's it.